Alright, let's see example 1. Okay, you can find this example in Sadiku page 487 to 488. Let's see the questions. In free space, the electric field intensity is given by E equal to 50 cos 10 power of 8t plus beta xy. The question is find the direction of wave propagation beta and the times it takes to travel a distance of lambda over 2, which is a half wavelength. Next, sketch the wave at t equal to 0 and t equal to t over 2. Okay, here is the answer. So basically the direction is negative x, beta equal to 0.333, and the time taken is 31.42 nanoseconds. But how to do it? Right, so first we see the equations. Okay, the E equal to 50 cos 10 power of 8 t plus beta xy. Right, from this equation, okay, like I said before that the E field normally is said to be oscillate along x component, but here it's different because we can see here we have y. So the E component is along y axis, and here we have x. So this is basically the direction of our propagations. It's not z, it's x. So be careful with the equations. Right, so here find the direction of wave propagation beta. So we see here, but we have to compare with the standard formulas. Okay, we go back here. Okay, this is a standard formula. We see that the E equal to the E naught, this is the amplitude, cos omega t minus beta z. So here is minus, and this is your propagation directions. Right, so when we compare with this, we have basically the plus here. So the direction of the propagation should be in minus x. Okay, so this is the answer. How about the beta? How to find the beta? So we can use the beta using the simple formula where the beta is equal to, we can use the omega divided by v. The omega is basically the radiant frequency and the v is the velocity. But here in free space, so basically the speed of electromagnetic wave is travel in the speed of light. So please remember the speed of light is basically c equal to 3 multiplied by 10 to the power of 8 meter per second. So basically here is the omega is 10 power of 8. This is omega because this is omega t. So here is 10 power of 8. Okay, so divide by 3 multiplied by 10 power of 8. We go back. 10 power of 8. So here we can cancel out. So 1 over 3 is equal to 0.3333. Okay, so we settle the two questions. And then next is the time taken to travel lambda over 2. Next, we want to find what is the time taken to travel half wavelength. So basically, for the electrostatic wave, we consider that the wave is in the form of the sinusoidal, like this. So this is a one complete cycle, and this is the lambda. So the half cycle will be the lambda over 2. So for the complete circle, the time taken to travel the complete circle is equal to the period of the wave, which is t. So basically for the half cycle, it should be t over 2. This is information that we have. So how to find the t? Okay, we can find by using maybe the t equal to 1 over f. Okay, and then we don't know about the frequency. We have the radian frequency. Okay, we have omega. Basically, omega equal to 2 pi f, right? So the f here should be omega divided by 2 pi. So we can put here. So it become, so it should be opposite. So 2 pi over omega. Okay, this is for the complete circle. So for the half circle, t over 2 is equal to 1 over 2 multiplied by 2 pi over omega. So we can cancel here. So equal to pi divided by omega equal to 10 power of 8. So here you got 31.42 nanosecond. Okay, this is the answers. Alright, so we go to the last question. Okay, we have to sketch the wave at t equal to 0, t equal to period over 4, and t equal to period over 2. Right, so how to do it? First of all, I would like to give you a general information on the relationship between the frequency and also the wavelength. So if you are using some modern instrument like the network analyzer or spectrum analyzer, normally we want to analyze what is the look of the frequency domain as well as the time domain. So if I have to sketch in 3D form, okay, this is a, let's say this is a frequency domain, the f or the omega, and this is the amplitude, right? So I can sketch another axis, okay, here. So let's say we have, okay, the first frequency, the f1, maybe we have the f2 or f3. Okay, in the frequency domain actually we can only see, okay, one straight line, something like this. Okay, something like this. We have the one straight line just to represent the amplitude of the signal at the specific frequency. This is in the frequency domain. For the time domain, what happened? We will see something like the continuous signal, something like this. Why this is different? Okay, so it's just like which angle that we will see. Okay, for example, this is a time domain t. So at the frequency 1, maybe at the lower frequency, we can see that the wave will going like this along this axis, and this one another wave. Okay, and this one we have another wave. Okay, if you look from this side, you can see, okay, the signal is like this. But if you see from this side, okay, what happened if you only see the straight line like this? Okay, the straight line. So that is the difference between the time domain and the frequency domain. So here you have to sketch in the time domain. You have to sketch the wave at t equal to 0, t equal to period over 2, and period over 4. So it's actually the time domain. But how to solve it? How to solve it? Okay, the next question, we want to sketch the graph at the t different time, which is t equal to 0, t equal to the period over 4, and t equal to the period over 2. Okay, it's always happen like this. I don't know why. Never mind. Okay, so we have to put all this time into the equation. The E is equal to the 50 cos the 10 power of 8t plus the beta z, the beta x in the direction of y. This is our original expressions, and we already calculate the beta, so you can use later on. So when t equal to 0, okay, so the expression become E equal to 50 cos beta x y. This is quite simple. So the graph become like this. So this is the direction of the E field, which is the y directions, the oscillations, and this is the direction of the propagation, basically x, right? And then the graph is cosinus, something like this. When you put the value, so basically here the value should be the lambda over 2, and here is basically lambda. Here is negative lambda over 2, and here is lambda. Okay, next we go to the t equal to period over 4. Okay, t equal to the period over 4. Okay, like I mentioned before, how to determine the period. Okay, the period t equal to period equal to 2 pi over omega, right? So the period over 4 is basically equal to 2 pi divided by 4 omega is equal to pi over 2 omega. So we have to put this value into our original equation. The E is equal to 50 cos the 10 power of 8. Okay, the 10 power of 8 is basically the omega. So multiply by pi over 2 omega. Okay, and then plus the beta x in the direction of y. So here we can cancel out. So it become the cos pi over 2 plus beta x. Okay, this expression can also be simplified because the cos beta x plus pi over 2 is basically equal to minus 50 sine beta x. So this is a trigonometry identity. Okay, so it's simpler to sketch. If we just sketch the sinusoidal graph, right? So negative 50 is basically is going down before it goes up. Okay, something like this. Here is the y direction, here is the x directions, and here is the, this is a pi, is no, this is a lambda over 2, this is lambda, okay, the full wavelengths. Here is a negative lambda over 2, and here is negative lambda. Okay, here is negative part, this is positive part. So we settle for t equal to period over 4. Next, for t equal to the period over 2. So similarly, the period equal to 2 pi over omega. So the period over 2 is equal to pi over omega. And the general expression E equal to 50 cos 10 power of 8 t plus the beta xy. So put t equal to the pi over omega. So here is also omega. So we can cancel here. So we got 50 cos beta x plus pi. Okay, plus pi. So when we have plus pi, we can simplify into E equal to negative 50 cos beta x. Okay, because plus pi. So to sketch, this is y, this is x, and then it's going down first before it going up. Okay, so sketch better. I forgot to mention about the amplitude, because the amplitude here is minus 50. The amplitude here is 50. Same with previous, I forgot to mention. So here, the complete circuit is here. Okay, this is a complete circuit for one cycle. This is basically the lambda over 2. This one is negative lambda over 2. Okay, this is lambda. This is we input others. This is a negative lambda. Right. So we settle our exercise for example 1.